Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is ET 122, Digital 2. Today we're going to talk about the design of synchronous counters. So we've previously discussed regular plain old synchronous counters, and we could make them count in a sequence from a low number to a high number, or using our up-down, we were capable of going from a high number to a low number. And that's well and good if you are counting in a regular sequence. Sometimes there's applications where you want to count in a different sequence. For example, you want to go every even number or every odd number, or you're counting in something like gray code where it is not a binary sequence. If you remember a gray code, like a binary sequence, that's a regular straight old binary. Gray code, remember, only one bit changes at a time. So that's gray, and that's binary. That was super easy. This, still easy, but not as easy. Basically, what you need to do is you need to develop some logic. As we've seen in our previous synchronous counters, we need to develop a logic to trick our flip-flops to toggle. And remember when I said earlier there's kind of an art to it? Well, this is where you go to art school. It's a very systematic means of doing it, and it's really not that complicated despite all the pages that it takes up in your book. If you think about it, there's only, regardless of whatever counter this is, binary or gray or whatever, or odd or even, there's only a bunch of transitions that can happen for any particular bit. It can be a 0 and it can stay a 0. It could be a 0 and change to a 1. It could be a 1 and go back to a 0. It could be 1 and stay a 1. And that's it, regardless of how complicated your binary counter or gray counter or even counter or odd counter or crazy sequence of numbers, whatever you want to do. These bits only make these 4 possible transitions: 0 to 0, 0 to 1, 1 to 0, 1 to 1. So that means our JK flip-flops, and this is what's referred to as the present state, and this is the next state. So given a present state of 0, and you want the next state to be 0, what is the settings for the JK flip-flop? Well, you're definitely not going to set it. So J has got to be 0. And you can reset it. But if it was already a 0, why are you resetting it? Or 1. So 1 or 0. It doesn't really matter what K is. So let's go ahead and replace that 1 or 0 with something we saw in the K maps earlier, with an X. Basically, don't care. We don't care what K is, because if it's a 0 on the present state and the next state, regardless of K, if it's got a 1 on it or a 0, it's going to stay a 0. Okay? Next thing here. So 0 to a 1. Well, it sounds like what we want to do is we want to set the latch. Okay? Or toggle it. Or a 0 just by setting it. So this sounds like it's another matter where the K doesn't really, what you put on the K doesn't matter. So now 1 to 0. Well, sounds like we're going to reset it or toggle it. So let's replace that right here with a don't care situation. Now the last one, when it's a 1, the present state is a 1 and the next state is going to be a 1. What are we going to do here? Well, we could definitely set it, as long as we're not resetting it. Or we could just leave it alone. So that sounds like this right here is another don't care situation. Okay? So just take this example right here, the binary 2-bit and our gray code here. Actually, here, let's just use gray code. So our present state 0, 0, 0, 1, 1, 1, 1, 0. Our next state, that's our present. Our next state, okay, that's going to be 0, 1. 0, 1. The next state after that is 1, 1. So on and so forth. Okay, so now what you need to do is just figure out, okay, how many flip-flops am I going to take here? Well, there's only 2 bits. In this case, Q0 and Q1. So it's going to take 2 flip-flops. Okay, we just need to figure out how to trick these flip-flops into toggling and setting and resetting. Okay, so let's draw our 2 flip-flops here. So here's our 2 JK flip-flops, and again we're going to design a synchronous counter. So we're going to go ahead and tie their clocks together. And now this is the lower order one, where that's Q0. That's a higher order one, Q1. And let's go ahead and just highlight here, Q1, Q0, Q1, Q0. Okay, so just to make this thing a little bit easier, we all know it's a synchronous counter. We're going to go ahead and get rid of these lines right here. Okay, now what we need to do is we need to figure out, given the present state and the next state that we want to go to, how do we hook up our J's and our K's for the individual stage? And this is the tricky part. Knowing this right here, that there's only 4 possible transitions that could ever occur for any crazy sequence that we develop here, we can figure out what each individual stage's J and K values are. Okay, so sometimes we want to toggle, sometimes we want to set, sometimes we want to reset, sometimes we want it to stay at the same. So how you do this is for each individual bit. No wonder why we only went with 2, huh? Yeah, let's do first 6-bit. This would take you all day. So 2 bits. For each individual bit, we just got to figure out, given the present state and the next bit, what would the JK's inputs on each stage be? I know that sounds like a mouthful, but let's take this in strides here. Okay, given our present state of 0, 0, and let's just keep our analysis to Q0 now. Given the present state of 0, 0, Q0 is going to be a 1. So that means it was a 0, and it's transitioning to 1. So we're obviously in this realm right here. Given a 0, transitioning to 1, that JK flip-flop input should definitely be a J1, and it doesn't really matter what the K input is. Okay? So what you start doing, start tossing these things into K maps, because it's going to get super complicated super quick. Okay, so what's our K map going to look like here? Actually, I'll just put it up to the top here. It's a 2-variable K map, Q0, Q1, 0, 1, 0, 1. And I'm going to call the output here as J0. And here's K0. You guys should remember K maps. I certainly hope you do at least. So as we stated previously, present state 0, 0. So that's our inputs. We're definitely in this circle right here. What do we want in those boxes? Well, for the J, we definitely want a 1. For the K, doesn't matter. Okay? So now, let's move on to the next guy here. So given present state 0, 1, what does Q0 do? Well, it stays a 1. So we're definitely right here. Okay? So given a 1, it stays a 1, and the J could be whatever, and the K is going to be a 0. So we've got to find it on the K map. Given present state 0, 1 right here, so we just put an X there. Given present state 0, 1, what's the K? It's a 0. So moving on. It may actually help to use colors or lots of paper, because this does get confusing. Okay, now given present state 1, 1, what does Q0 do? Well, it transitions from 1 to a 0. So 1, 2, 0, we're in this guy right here. So J, X, don't care, K, 1. Okay, where are we on the K map? We're in this box though, because remember, gray code. Okay, so J is an X, K is a 1. Moving on to the next guy. So given present state 0, 1, what does Q0 do? It stays a 0. So we're right here. Okay, so J is a 0. K's that don't matter. Okay, we could go ahead and figure out some of the logic given the K map as it exists right now, but we've only done one stage, because remember, we just figured out the logic for stage 1 right here, because we only did the analysis for Q0 so far. So let's save that until we get Q1s. So now what Q1's going to do, we have to do the exact same analysis. Given the present state, these present states right here, we have to do the analysis for Q1. So to do that, I'm going to make a little bit more room by shrinking this diagram down. Then I'm going to move these guys. Oops. Or I'll do this, I'll move them over. There you go. Here's our J0. Here's our K0, which we previously developed. Just giving us a little bit more room. So let's go ahead. We're doing the analysis, like I said, from the perspective Q1 now. Okay, so got to do the whole thing again. So let's make K-maps again. And that's for J1, and that's for K1, which, if we remember right, is this stage's J and K. So we got to figure out the tricky means of getting this guy to toggle when we want it to. Okay, so from the analysis of Q1's perspective, how do we do it? Okay, given present state 0, 0, yeah, you got to go through the whole thing again. Given present state 0, 0, which is putting us in the upper left-hand corner of our K-map, Q1 is going to stay the same because it's at a 0 and it's staying a 0. So we're in this realm right here. Okay, so given that, J going to be a 0, K don't care. Okay, given state 0, 1, what does Q1 do? Well, it goes from a 0 to a 1. So we're in this one. So that is J1, K, don't care. So that's upper right, because remember, this is present state right here. So 0, 1. Okay, now we're moving on. Given present state 1, 1, which is the lower right of our K-map, Q1 is a 1, and it stays a 1. So we're right here. So that means J doesn't matter, K 0. As long as that K is a 0, that's going to stay a 1. So now, last one, given present state 1, 0, Q1 was a 1, and now it makes a transition to 0. So we're in this state. So JX, K1, doesn't matter. Okay, now you can start. I know some of you guys were itching to do the K-map analysis. Now you can do the K-map analysis. Okay, given this arrangement of 1s and 0s in our particular K-maps for each one of our stages, what is, and making use of the X's, what's the most efficient means of doing it? Well, let's start with J0. If you remember right, is the first stage's J input. What I would do, I'm going to do this in red, I would just group these guys right here. Because Q1, excuse me, that's not Q1, right here, 0 is the only thing that's constant in there. Yeah, you could group this guy right here, but again, K-maps, you take the least number of groups. The biggest group, 2, remember? That's why I did the 2 of those. Okay, so for K0, what are you going to do? You could do a bunch of different things here. What I would do, here, 1 second. I would probably just do this guy right here. And again, it's the biggest group, the smallest number of groups. And what is that? Well, the only thing that's constant is Q1 being a 1. So what's the logical expression there? Just Q1. Okay, so it sounds like the inputs to the first stage, J and K inputs, are actually the outputs of the second stage here with a little bit of logical manipulation, one of them being a not Q1. And we can go ahead and implement this, but we haven't done the analysis for J1 and K1 yet. So let's do that one first before we actually start stringing these things together. Okay, so from J1's perspective, what are we going to do here? I would group this guy right here. And what's that? That's Q0, because Q0 is constantly staying at a 1. So K1, what I would group is this guy, and that's a not Q0. So again, when do these things toggle? Well, they'll be, well, we'll implement these things. And we'll see when they toggle and when they set and when they reset. So now what we need to do is, like I said, is going to implement these things. We need to take our logic that we developed for our J1, K1, J0, K0s and just hook it up to our JK flip-flop arrangement. And I'm going to go ahead and draw that down below here, which looks terribly simple, doesn't it? Yeah, I'll go ahead and add a clock to make that even simpler looking. Yeah, it's a mess of wires right now, but what we'll do is just do a super quick analysis. We'll do this stage by stage. That's why I use a 2-bit for this example here. So we can see, okay, what each one of these JK flip-flops are doing. Yeah, I know it's super confusing here. Let's go ahead and get rid of some of these wires. Well, didn't mean to do that. So what we're going to do is just kind of do this on a step-by-step basis here. Okay, so let's start off in present stage 0, 0. And we'll do these by stages. So for stage 1, JK, excuse me, stage 0, stage 1, MSB. Okay, given present state 0 and 0, what is the JK flip-flop inputs for our LSB stage? Well, let's look at the logic that we developed. I know you could follow the wires around, but that would be confusing. Let's just look right here. It's not Q0, excuse me, not Q1 and Q1. So Q1 is this guy. So a not Q1 is a 1, and a Q1 is a 0. Okay? So what is this stage going to do? Well, it's going to set, okay? So that's its action. The next clock pulse comes along, it sets. Keep that in your mind for a second. We're going to work on the second stage. Okay, given inputs Q1 for the present state was 0, Q0, 0. What does the second stage do? Well, its toggling inputs, excuse me, its JK inputs are respectively Q0 and not Q0. So Q0 is a 0, not Q0 is a 1. So what does this stage do? It resets. Okay? So, given the fact that the first stage is setting, the LSB is setting, and the MSB is resetting, what happens when you're given that? Well, setting the LSB makes it a 1. Resetting the MSB, it's already a 0. It's a 0, 1. You've made that transition from, according to our gray code, 0, 0 to 0, 1. Ta-da! That one wasn't super hard because all our other counters we've already done this trick. So this is kind of one of those, okay, yeah, so you change 1 bit. Not too exciting. But now remember that the magic comes in binary, excuse me, in gray code. That's transition 0, 1. It doesn't go to 1, 0. That's an ordinary counter trick, but we're making a special counter. It goes 1, 1. So given our present state of 0, 1, we want it to ideally get to a 1, 1 state. Let's make sure it happens. Okay, so given 0, 1, what is the inputs for our first stage, our LSB stage? Well, again, it's the J is not Q1, as we discussed, and our K is Q1. So not Q1, 1, 0, sets it. Okay, now JK, excuse me, the MSB right here, what are its inputs for the JK? Well, it's Q0 and not Q0. So Q0, though, is now a 1. So it's opposite previously. 1, 0. This also sets. So what happens when you make this transition when Q0 is a 1 and it's going to set? Well, it stays a 1. And when Q1 is a 0 and it's setting it, ta-da, you've made the transition to 1, 1, which was the trick in gray code. So now, given 1, 1, this, by the way, is just a means of testing it. You've done it correctly. You're just going to make sure you've done it correctly. Just walking through. You don't have to do this analysis every single time. I'm doing this for your benefit because I love you. Okay, 1, 0. We want it to go. Excuse me, 1, 1. We want it to go to 1, 0. What are the inputs on each one of the stages? Okay, so again, LSB stage. What are the J inputs? It's not Q1 and Q1 for the K. So not Q1 is a 0 and a 1. So what's going to happen here? Resets it. Okay? So given a 1, it's going to reset it to a 0. Now, let's do for the MSB stage here. It's going to say, okay, J1, K1, what are its inputs? Well, it's Q0 and not Q0. So Q0 is a 1, not Q0 is a 0. Again, it sets. It's setting a 1, so it's already a 1. 1, 0. Ta-da, we've done that transition. Now, 1, 0. We want to make sure we're going to recycle to our 00, just to make sure. Okay, what are the inputs for this stage? I'm just going to go ahead and jump it. So J0, K0, it's going to be our not Q1 and Q1. That's going to reset it. Oh, excuse me. So it's going to reset. Well, it's already a 0, so resetting a 0, it's just a 0. And now what do we want to do for our second stage? Well, it's Q0 input for the J1, not Q0 for the K1. Oops. So we're looking at this bit right there. Oops, I'm going crazy, guys. So we're looking at this bit here. So not Q0, that's a 1, 0. Basically, it's going to reset. It's resetting this bit right here, 0, 0. We've made the transition back to 0, 0. And we don't have to do this thing again because we're back up to there again. So this long exhaustive analysis right here is just a means of testing it to make sure that your JK flip-flops are properly toggling, setting, or resetting when you need it to. So all we did right here was just, again, in summary, we're just going through each one of the present states for each one of the bits and using this basis right here, the fact that there's only 4 possible transitions, determine the JK inputs for each one of the particular stages. And now we implemented, and bonus round, we tested it. So now to make sure that this horse is properly beaten, let's just do an example. And I'm going to not do it as thorough as the last one right here. We'll do it a little bit quicker. Let's just make a counter. It's a 3-bit counter. And we wanted to count it only the even numbers. We could just easily do odd or some crazy sequence of numbers. But we want to go ahead and design a counter that does only even numbers. So our states are 0, 0, 0, because that's 0. Let me put that on this side. Then we want it to go to 2. Then we want it to go to 4. Then we want it to go to 6. Then we want it to recycle. Okay? So what we'd have to do is, given the present state right here, our next state, and you want it to recycle, what we need to do is go ahead and develop our truth tables, our K-maps for each one of these bits. And let's call them again, Q2, Q1, Q0, Q2, Q1, Q0. We need to go ahead and figure out what the JK inputs are for each one of the particular stages. How many stages do we need? Well, it's 3 bits, so obviously we're going to need 3 JK flip-flops. But remember how I said there's a little bit of an art to this thing here? Just look at Q0. It's never changing. It's always a 0. So yeah, you could do this whole analysis, but I guarantee you, and remember, this is a 3-bit K-map because now our present state has 3 bits, Q2, Q1, and Q0. Your J input for the first stage. Let's just do this and I'll show you exactly what it's going to look like. So I guarantee you what's going to happen is if it's always a zero, it's always a zero, you can never be resetting it. And technically I should be having X's in there. But why not just make this thing, I'm going to go ahead and do it. Why not just make this thing all ones? You're constantly resetting. You're constantly resetting Q0. Now I'm going to save you even some more time. Look at stage 2. It's constantly toggling, okay? So you can save yourself this whole step just by making J1, 1, K1, 1. So, by the way, so I'm constantly putting first stage J at 0, constantly putting first stage K at reset, constantly toggling my second stage. So you've got a super quick shortcut here. That becomes the art of it here. You got to recognize these sequences. Okay, now this guy. Okay, Q2. Okay, I admit there's a little bit more analysis that needs to go into this guy. So let's go ahead and do our K-map here. So Q2, Q1, Q0. Okay, so we already figured out for our first two stages, that's super easy. What we want to do is from the perspective of this guy here. Okay, given present state 000, it was a 0, it's going to stay a 0. Let's draw our handy dandy little diagram right here. You should always have this with you. So there we go, that's our handy dandy little diagram right here, showing us all 4 possible combinations of transitions and what the J's and K inputs should be for that stage. Okay, so 000, again, we got 000, and Q2 was a 0, and it stays a 0. So we're right here. So J, by the way, that's J, oops, J2, K2, J is a 0, K, don't care. Now let's go ahead and do the analysis for this present state, which we're missing a bit for some reason. So given this present state right here, it's a 0 and it's going to 1. So now we're here. So we want J1 and K doesn't matter. Okay. Oops, what am I doing here, guys? I just went ahead and did full auto because you'll see it here. What state are we in? What's our present state here? Our present state is 0, 1, 0. 0, 1, 0. Okay, so J1, J2, 1, K2, doesn't matter. Reason why? Why are we not doing that block right there? Well, because it's an odd number. That's a 3. Or excuse me, that's a 1. Remember, our counter is only going to see states 0, 2, 4, 6, and back to 0. It's an even number. So there's a couple, you'll see what happens in those columns right there. Okay, so what is our next present state? Our next present state is 1, 0, 0, which is that box. And at 1, 0, 0, Q2 was a 1, and it stays a 1. So we're here now. And we want J, doesn't matter, K, 0. Last state here, 1, 1, 0, Q2 is a 1, and it's making a change to a 0. So we're right here. Now, like I said previously, we're never going to have situations where ideally, we're never going to have situations where we're going to have an odd number. So there are no possible previous states of Q2, Q1, Q0 ever being odd. So what we could do is just say don't care, 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 don't care. So now we go ahead and group our K-maps here. And how I'm going to do it is this way. I know that one's got to be a 1 right here. So I'm going to make it a bigger group though by grabbing all that. What's the one thing that stays the same? That's Q1. Same thing over here in K-land. I'm just going to go ahead and grab this guy right there. What's that? That is also Q1. So it looks like we've developed the logic for our particular stage, what we're interested in. And notice that we've already done the LSB, the guy in between, and finally our MSB. So as complicated as an even counter may sound, you're skipping state 1, 3, 5, and 7. It's really not complicated once you actually go ahead and do the logic for it. So let's go ahead and I'm going to implement this thing and then we'll do a test, and nowhere near as exhaustive as the last test. So I'll go ahead and draw what it looks like. And again, these are synchronous counters. So all our clocks are put together, but I don't want to complicate matters, so we're going to go ahead and actually remove those lines. Okay, what was our first stage? Our first stage was J0 is constantly at a 0, K0 is constantly at a 1. So what's happening here? This one constantly resetting. Second stage guy, he's constantly toggling. And then this guy right here, our MSB, what is his inputs? Well, its toggle inputs just so happen to be Q1 for the J and Q1 for the K. So by the way, that's Q1, Q0, and that's Q2. So let's do, that is our implementation of it minus our clock. Now what we could go ahead and do is give this guy a test here. Okay, give this, let's say he's sitting at 0, 1, 0. So its present state is 0, 1, 0, i.e. a 2, and we should ideally see this transition to a 4. So first, let's do Q2, Q1, Q0. That's our present. And our next state, Q2, Q1, Q0. Let's do it stage by stage. Okay, so first stage, constantly resetting, 0. Second stage, constantly toggling, 0. Okay, next, Q2. Well, what's happening here? The inputs for the J and K for this MSB stage is this guy right here, Q1. So it sounds like it's a toggle, because if both J and K are 1, it's going to toggle. So it's going from a 0 to a 1, and we've made that transition from 2 to 4. So nice, we're looking good there. So now we're going to go on to the next stage, given 1, 0, 0. Again, constantly resetting, constantly toggling. Now the inputs for this MSB stage is Q1. Okay, Q1 is a 0, so that means stay as it is. We've made that transition from 2 to 4, and now we're at 6, just like we wanted to. And if we did it again, we could go to 0. So all it is a super quick test just showing you that your your system of toggling and setting and resetting is working. But now, let's say it just so happens to get off the track just by accident. Somehow Q0, Q1, and Q2 get inadvertently an odd number stored in there. Ideally, this system should be self-correcting and get back to at least the right track within a couple steps. So let's see if that happens here. So let's say inadvertently, just so happens you pull a flip-flop off the shelf and Q0 for some reason has a 1 stored in it. So what we're sitting in a situation where there's a 7. That's a wrong situation. So we want to go ahead and see when the next clock pulse comes along, what happens here. Okay, so Q0, constantly resetting. So it takes that 1, makes it a 0. Q1, it's constantly toggling, makes that a 0. Now Q2, its J and K inputs are toggle mode. So it takes this 1, makes it a 0, boom, we're back on track with a 0. Sometimes, given a more complicated counter, it may take 2 or 3 steps off in no man's land before it gets back online. But this here is a situation where it just came up with only 1 error state, in this case a 7, immediately make a transition to 0, and then ideally, if we've done everything correctly, it should go to 2 to 4 to 6 and keep on going. Okay? So both these counters that which we just designed here are 2-bit gray counter, and in this particular case, our 3-bit even counter are examples of what are called Moore circuits. These are only dependent on the present state. Okay, the only thing that influences the next state is the present state. It's only looking at itself. There's something else called a Mealy circuit, which we're going to be using for the traffic control signal. And what that is, it is taking into account external inputs. So what you could imagine here, its present state and, let's say, in this particular case, no, I'm not going to use an X because that's a bad choice. I'll use a Z. That's an external. Okay, so there's an external input as well as the present state, which determines the next state. Okay, so what you're going to have in this particular case, 3-bit present state and a single external variable, what you're going to get is a 4-variable Carnot map. And there's an example in your book that is an up-down counter, up-down gray counter, which is actually pretty cool feature. Basically, it's a 3-bit present state and a single external input variable, which is your up or down command. And what it does, it just walks you through the creation of this next state logic for the JK flip-flops. Again, not as complicated as it seems at first if you approach in a very systematic manner. And again, what's the system? All dependent on this right here. Those are the only 4 possible transitions right there. All you do is just walk through each one of the bits for given the present state, or in the case of a Mealy circuit, some of the external variables, and determine the logic for each one of the stages of the JK flip-flops. And for smaller things, you can kind of run through a couple tests to make sure you've done it correctly.